Hello and welcome to tribetopper.com.
In this video, you're watching the past paper solutions for IB Physics. So here we have the question. It says a closed box of fixed volume 0.15 meter cube contains 3 moles of an ideal monatomic gas. The temperature of the gas is 290 Kelvin. So we are given the parameters V, that's the volume, 3 moles, that is N, the number of moles of the ideal monatomic gas, and the temperature of the gas is given, that's T. So we have V, N, T, and R, the universal gas constant we know is 8.31. Therefore, we can solve this question now applying the ideal gas equation. So you would write the answer as that ideal gas equation gives us PV is equal to nRT. So PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. Therefore, what is P? P can be calculated by keeping here on the left hand side, and you get nRT upon V, and just plug in the values for N as 3 into R as 8.31 times T as 290 Kelvin, and this whole thing divided by volume, that is 0.15 meter cube, and solving you're going to get 48,000 Pascal, or we can also write it as 48 kilopascal. So that's the whole thing you have to do here. And in the next part we have when the gas is supplied with 0.86 kilojoules of energy, its temperature increases by 23 Kelvin. So we are supplying Q, the energy of 0.86 kilojoules. The temperature increases by 23 Kelvin. That means you have delta T, that's the change in temperature, and the specific heat capacity of the gas is 3.1 kilojoules per kilogram per Kelvin. So we have C. Now we are given all these 3 parameters and you have to calculate in kilogram the mass of the gas. Now we will use the equation Q is equal to, you write since Q is equal to mc times delta T, therefore m would be equal to, rearranging the terms, that will give you Q upon C delta T. Now just plug in the values of Q. It's 0.86 kilojoules, so we want the answer in SI units, so you will write this as 860 joules upon C, that is also 3.1 kilojoules. So when you multiply it by 1000, you get 3100 joules times the change in temperature, delta T, is 23, and when you solve this you get 0.012 kilograms as the mass of the gas. In the second part of B, they are asking determine in kilojoules the total kinetic energy of the particles of the gas. In order to find total kinetic energy of the particles, and see, this is a 3 marks question, so how are you going to write the answer? First thing is you mention the formula that we know that average kinetic energy per molecule. So what is the average kinetic energy per molecule? We calculate this as 3 upon 2 times kT, where K is Boltzmann constant and T is the total temperature. So what is the temperature now? We have already seen in the previous part that the temperature was increased by 23. We started with 290. Therefore, T in this case would be 290 with what we started plus 23 when the temperature rose. So you have the temperature now as 313 Kelvin, and K, the Boltzmann constant, you will also mention K, the Boltzmann constant, its value is 1.38 into 10 to the power minus 23. So we have both the values, therefore we get the average kinetic energy. You will write as Ke average per molecule is 3 upon 2 times K, that's 1.38 times 10 to the power minus 23 times T, that is 313. So multiplying this, you would get 6.5 into 10 to the power minus 21. Now this is the average kinetic energy per molecule. Now what is the number of molecules? N, the total number of molecules is 3 moles of gas is there. We know that 6.02 into 10 to the power 23 is the number of molecules in 1 mole of a gas, that is Avogadro's number. So you multiply this with the given moles, that is 3. So we get 1.8 into 10 to the power 24. That's the number of molecules. Therefore, the question asks you the total kinetic energy of the particles. Therefore, the total kinetic energy of the particles will be the total kinetic energy of the particles or all the molecules would be the average kinetic energy per molecule into the number of molecules. So we have 6.5 into 10 to the power minus 21 as the average kinetic energy per molecule multiplied by the number of molecules, that's 1.8 into 10 to the power 24. And on solving this, you just get your answer straight away, 12 kilojoules. And the last part of this question says explain with reference. So with reference to the kinetic model of an ideal gas, how an increase in temperature of the gas leads to an increase in pressure. Now we know that an increase in temperature implies larger kinetic energy of molecules. This leads to increased force or momentum transfer to the walls of the container. Since pressure is force upon area and area is going to remain constant, therefore for an increase in force there will be a proportionate increase in the pressure. So you have to write down this complete answer. I hope you understood how to attempt the questions. I hope the video was helpful.
Please follow us on Instagram, Facebook, and Twitter at tribetopper.com.